Perfect. So welcome everyone to the November 2021 TEPS seminar featuring Professor Aaron Boley, one of the co-Is of the TEPS program. I'm going to pass it off to Simone, who is one of Professor Boley's trainees, to introduce Professor Boley. So Simone, take it away.
Thanks. So Dr. Aaron Boley is an associate professor at the University of British Columbia and Canada Research Chair in Planetary Astronomy. He's also the co-director of the Outer Space Institute, which is super relevant for this talk, which is a transdisciplinary organization that addresses challenges associated with new space. Before joining UBC, he was a NASA Sagan Postdoctoral Fellow at the University of Florida and a postdoctoral researcher at the Institute for Theoretical Physics at the University of Zurich. His Professor Boley's wide range of research interests include planetary dynamics and formation, astrophysical disks, meteoritics, and space sustainability. He can often be found chatting about exoplanets and space policy, and in Zoom meetings, you might be lucky enough to catch a glimpse of his adorable puppy, Luda.
Thank you very much, Simone. And thank you everyone for joining. This is a topic that I'm very passionate about, space sustainability. And I think it's something that we absolutely need to talk about, particularly with the event that just happened on Monday with the Russian Federation destroying one of their own satellites and endangering the lives of astronauts, taconauts, and cosmonauts, as well as the orbital infrastructure. And I will talk a little bit about that moving forward, because that's just one component of a bigger picture. I invite everyone to use the chat to ask questions as we go along. If I'm able to work in an answer to the question, I will try to do so. Otherwise, we could take those questions and we can answer them at the end. I tend to go on and on about things, so that works against me, but I'm going to try to save time at the end for lots of discussion. So this is intended to be a broad overview of many topics related to space sustainability. So where I would like to start then is with sharing my screen. Okay, and now that that's shared, do you see a garbage truck collecting satellites, broken satellites? Okay, great. So this is some artwork that was done by the Globe and Mail for one of our pieces that went in talking about space debris. We need to first begin with collective action problems, collective behavior problems. This is something that we're all familiar with, and we have to deal with it in multiple ways. The problems tend to have a very similar characteristic that's often tied to this idea that's known as the tragedy of the commons. This idea is you have a resource that everyone can use, and your impact on that resource is really small, very small. But the collective impact of everyone who comes to the conclusion that your individual impact is small has a very pronounced effect. This idea that there's no way humanity could dump enough plastic into the ocean to make a difference has come back and shown that no, we can, in fact, do that collectively. This idea that there's no way we could dump enough material into our own atmosphere to change our climate is something that has met so much resistance, yet we just keep doing it. And even though we're now finally getting to people who for long said, no, there's no way you could be doing this, the action to actually rectify the situation is slow and difficult. But it's not always this way. So when the ozone hole was identified, or the development of an ozone hole was identified, there was, in fact, swift action that took place in order to address this collective behavior problem, where again, an individual doesn't have a very large impact, but collectively, we actually have quite a substantial impact on the environment. And Canada can take a lot of pride in this as well because of the major role that it played in the Vienna Convention on the Protection of the Ozone Layer and the Montreal Protocol. So these problems, as daunting as they are, they can be addressed. Yes, we keep hitting this wall with climate change, but we do know through the ozone layer that we can address these type of problems. So that's one thing that I want us to keep in mind as we go through. Now, with space, there was a question before Sputnik about what is the jurisdiction of space? Can a state claim the jurisdiction of directly above it? How far does that jurisdiction go? Well, Russia launched Sputnik, and that immediately solved that question, that a state does not have jurisdiction over the orbital environment, that you can't claim that. So Russia or the USSR set that idea within international law. And then other states then followed suit, United States, Canada, the United Kingdom, for example. And there was a big rush then, because this was an area beyond jurisdiction. So no one had direct control over it, but you wanted to exert your dominance over that particular region. And so states were very quick to then act. And they did a whole bunch of things that I think many people don't realize actually occurred early within our use of space. Project Westford. So the United States military wanted to have very stable long distance communications. At the time, the idea was just to use radio signals that bounced off the ionosphere. But the ionosphere was too variable to have that be as reliable as what was needed. And so engineers came up with the idea, well, if we don't have a reliable ionosphere, let's just make one. And so Project Westford was born. And the idea is actually quite simple. Just dump a whole bunch of dipoles into orbit so that now you can send a radio signal, bounce off this reliable dipole sphere, and you could get signals anywhere else in the world. And so the first attempt to do this was in 1961, and that failed. It had there was major outcry led by astronomers, by radio astronomers, by optical astronomers who are worried about optical flashes from the dipoles, and also just scientists throughout the world who did not think that one nation should unilaterally be polluting the orbital environment in the way that was being proposed. So what happened in 1961, they built everything, they sent it up, they tried to release the dipoles, and the dispersing mechanism failed. And so things were clumpy and didn't actually make it very far. So that didn't work. They retooled everything, and in 1963, they did in fact successfully deploy 500 million copper needles. And some of those are still in orbit today because they didn't completely disperse. Most of that material has deorbited at this point, but some of it remains in orbit. So did it work? Well, kind of. It did. There was this kind of temporary shield that, or ionosphere that was usable. But the thing that is frustrating about this is it was made obsolete before the second attempt. And the reason it was made obsolete is because the first communication satellite was launched. So, there's this huge change in the orbital environment that was just immediately unnecessary. This is not the only problem that was happening. In the late 50s, early 60s, the Cold War was really problematic with all of the nuclear weapon tests. And both the USSR and the United States wanted to know what would happen when you detonated a nuke in space. And so they were doing that. There were multiple tests. I'm going to just read this excerpt from something we recently published in the Globe and Mail. The sky above the Pacific Ocean turned red on the night of July 9, 1962. In Hawaii, street lamps went dark telephones stopped working, and burglar alarms began ringing, all because of a mysterious electromagnetic pulse. High above the ocean, at least 6 satellites were disabled. Only a few people would have understood what was happening. Fewer still would have realized that the course of humanity had just changed. We purposefully wrote that to sound like it was the beginning of some sci-fi novel, but it wasn't the beginning of some sci-fi novel. What had happened was the United States government had just detonated a 1.4 megaton nuclear bomb in orbit at about 500 kilometers. And that image you can see is the image taken from Honolulu of that explosion. And the electromagnetic pulse did knock out telephone capabilities and did cause some malfunctions throughout Hawaii. It wasn't this complete blackout, but it did create problems. It created auroral emission, and it knocked out that very first communication satellite. So they destroyed a satellite in this particular test. And there were 6 satellites that were ultimately critically damaged. Now, what was interesting about that is the response was pretty swift. So some context, the 1959 Antarctic Treaty was just finalized, and states were looking over and beginning to sign and ratify it. And in there was this interesting idea of how you govern something that is beyond, that is an area beyond national jurisdiction. And it had these ideas of freedom of scientific exploration, freedom of use, and non-appropriation. So that's going to be important context. After Starfish Prime and the USSR and the United States were detonating things in space, there was a very strong pushback among the world, and including the USSR and the United States, that, we shouldn't be detonating nuclear bombs in space. And so 1963 led to this limited nuclear test ban. It's limited in that you couldn't test a nuclear weapon if it's in space, if it's in the ocean, in the atmosphere. Underground testing was not prohibited at that time. This became a very important treaty because it immediately then led to the groundwork of the Outer Space Treaty. So the Outer Space Treaty can see origins within the Antarctic Treaty, the Limited Test Ban Treaty, as well as Project Westford. And the ideas in there are very important for even today's use of space. And the Outer Space Treaty led to 3 additional treaties, and I've shown them here. The Rescue and Return Agreement, which states that if an astronaut is in distress, then there is a duty among those who can to lend aid as practicable. And kind of when it was written, the idea is, if an astronaut or astronauts have a splashdown or they have landfall somewhere that is in a precarious situation, states need to come in and help out. But it's been extended to also space as well. If something happens in space, there's a duty, if you can help, to help. Liability Convention 1972, Canada has played a central role in this because we had nuclear waste spread over the Arctic as a result of a USSR satellite reentry. It had a reactive core, and it just spread nuclear waste among the Arctic. The only time that this treaty has been used. And then there's the Registration Convention, which I'm not going to go too much into that. It's an important treaty, but there's not too much to discuss here. The Outer Space Treaty, which is the backbone, has several important, the whole thing's important, but there are several articles I want to highlight here. Article 1. Okay. So the exploration of use in outer space shall be carried out for the benefit and interest of all countries, irrespective of their degree of development. So the Outer Space including the moon and celestial bodies, shall be free for exploration without discrimination of any kind. And there's freedom of scientific investigation. This is how the Outer Space Treaty starts, and the preambular portion emphasizes this broad idea and context. The Article 2, this one is actually a lot of has a lot of discussion regarding the use of the moon, and most recent discussion with the Artemis Accords and the Sino-Russian Pact of actually mining the moon and using those resources to further space exploration or for commercial gain. And this article states that you can't appropriate, and importantly, by means of occupation or by any other means. So you can't have any type of de facto occupation or claim of sovereignty. You don't have to simply stick a flag in it and say, I own this. If you do things like you own it, then that can be contravening this particular part of international law. Speaking of international law, the outer space law, as set forth by the Space Treaty, is part of international law. It's not separate from it, and that's what Article 3 emphasizes. So as international law becomes developed, that's also developing part of the interpretation of space law. Article 6 is very important because this comes into the context of what do commercial operators do? What are the rights of commercial operators? But here's the thing. So commercial operators are not directly regulated by the Outer Space Treaty. But they are directly supervised and authorized and monitored by the states in which they are incorporated. And if it's an international entity, then by their respective international regulatory bodies. So a state is ultimately responsible for supervising any given company. So companies still are bound by the provisions of the Outer Space Treaty, but in a way that is interpreted by their nation, by their state. So it's up to the state to do the supervision. Article 9, for all the planetary scientists listening, this is an incredibly important article because it is the foundation of planetary protection. It's this article that's led to the COSPAR guidelines of planetary protection, and it's what most states use. What will become very important for the rest of this talk is the idea of due regard. And that is, so when you're exploring space, when you're using outer space, it needs to be done in cooperation, mutual assistance, and the activities, including on the moon and other celestial bodies, must be done with due regard for the interests of other states. So anyone who's doing stuff in outer space, you're free to explore and use space, but your freedom to use and explore space is not absolute. You can only explore and use space insofar as you do not prevent others from also using and exploring space. Now, that's all I want to say about the Outer Space Treaty at the moment. For sources of international law, so this is a question I often get. So what about a state that hasn't signed the Outer Space Treaty, for example? Well, treaties are only one part of international law. And from Article 3, we know that space law is part of international law, not separate from it. And so if we look through how we interpret international law, then interpreting space law has to be interpreted along with how we do international law. And there you have treaties. So that's, I think, very clear. Countries have signed something and said they're agreeing to these terms. But then there's this idea of customary international law. That is, the collective actions of states can set law. And so if enough states do something, then that's interpreted to be law, international law, and that's applied to all states, regardless of whether that state agrees or not. An example is actually the United Nations Convention of the Law of the Sea. The United States has not ratified that, but it abides to most of the provisions under the law of the sea, under customary international law. Then there's something that is a little bit trickier to get through, but the idea is that there's this generalized principles of law recognized by civilized nations. I like to use the original context of this to emphasize how outrageous it is, and that this idea was certainly developed by Western civilization by putting in civilized nations. It is the case now, though, that civilized nations should be read as community of nations. So it includes all nations. So if all nations have a law that says you can't advertise something in space, you can't have giant space banners, okay, that doesn't exist. But if that happened, then that would be deemed as international law, customary international law. Enough states did that. I'm going to pause here. I'm going to get back to more direct space use, but are there any questions about the law aspect? Because this is going to be a recurring theme as we go through. All right. Again, if you do have any further questions with that, put it in the chat, and if I need to come back to it, I definitely can. Okay. So, immediate questions that I have when I look at all this is, how do we actually balance this freedom of exploration with due regard and avoiding harmful interference? And another one is, what does environmental law play? How do we actually understand our use of space in the context of environmental law, because international law or space law is part of international law. So this becomes, I think, this tension or this problem that we have becomes very clear in this video, which is admittedly a bit dated now. So what this is showing is, at the time, all of the satellites that were all the new satellites that were filed. So this does not include everything that was already in orbit in 2017. I'll get to that. But these are just all of these so-called mega-constellations. And this is what we can expect if we actually have a world in which there are about 100,000 satellites. And this is showing all these different constellations coming online with their global coverage. They all have different orbital shells. Some of those orbital shells are in fact overlapping. They have different inclination distributions because they have different missions. And it's potentially quite a problem for a number of reasons. One last one here. So at the moment, and I'm going to come back to this, there are about 65,000. There are 65,000 satellites that have been approved and are quite possible for being put into orbit. And this is by companies like SpaceX with Starlink, OneWeb, Amazon, Kuiper, and then StarNet, which is a Chinese mega constellation, which will be China's answer to Starlink. So I've used the term mega constellations. A couple things here. And that's widely adopted in the media. The companies that actually operate mega constellations don't like that term. They view it as very pejorative. I don't care. There's the technical community likes to use large constellations in order to avoid that issue. And in the astronomical community, with all the discussions with the operators, we often call them satcons, just for satellite constellation. Both of those terms, though, downplay just how many satellites are going to be going up compared with what we have today or what we had in 2019. And then I have a little bit of humor there in that last one. All right, so there's this idea of new space, and new space is this context it's very loosely defined but it's just where you have a whole bunch of commercial operators that are now being the dominant factor in space flight. Instead of being led by national interests, it's now being led by commercial interests. And this has a lot of really cool possibilities, and particularly in terms of making space very accessible to everyone. But it also comes with all the collective action problems that can arise when we start using a resource without having a mechanism that actually coordinates that resource globally. And so this comes back to this idea that, we think things are so large that our actual use can't matter or won't matter, but that's just not the case. What we're seeing here is the density distribution of material in orbit as of this October. Okay? And so there are many different things here. So the pink is spent rocket stages. This is the density of spent rocket stages. And the way this is actually made is it takes the orbits and averages them in spherical shells, and the contribution of a particular body to a given shell depends on the fraction of time it spends in that shell. So this is a very average view of it. Okay, but even with that, there are a couple things to note. Like there's this peak here in what's called the track debris. So these are things that are 10 centimeters and larger that are all fragments and junk from the uses of space. This does not include derelict spacecraft and rocket bodies, but that's also a form of debris. So you have this huge peak, and so this is one of the most dangerous places to operate in terms of the debris field. Right here, this very narrow spike of high density, that is Starlink. The first shell of Starlink is complete with 1,600 satellites. And that has this very high density, something that we have never seen before. And we're going to be playing out this experiment as we move along. We could come back more to this as we move on. One thing to really emphasize here is that satellites are not evenly distributed in the orbital environment. They have missions, they have altitudes that they need to use in order to do a certain mission. And because of that, the orbital environment is easily crowded, even though it's large. If we go ahead and extend to what things might look like if all of these mega constellations go up as filed, and I've only included the 65,000 that I think are actually likely to go up, then this is what that orbital environment looks like. So you have these very high spikes of high density that, again, much different from what we've seen before. And this spike here is only a little bit larger than the current SpaceX spike. And it will be a little bit larger because different operators are going to be using those same shells. We can take a look at the cumulative growth of objects in orbit to get an idea of what's been happening. And I'm showing track debris, payloads. Payloads includes active and defunct satellites, and then rocket bodies. So the black here is just everything that's been cataloged, that's gone up. The green is what's re-entered. Okay, and then the magenta is the difference between those two. So that's what's currently on orbit as a result. And we've just been steadily increasing the amount of debris. The payloads becomes really interesting because of this particular feature here. And then our rocket bodies, the junk that we've been putting up in orbit has also been, or the rocket body junk that's been going up in orbit has been steadily increasing. These rocket bodies are very massive. You can think of these as the asteroids of the near Earth orbital population, in that these are going to be, these are major sources of additional debris. That jump right there, that's the 2007 Chinese anti-satellite test. This is where China, to demonstrate its anti-space, counter-space capabilities, destroyed one of its own satellites using a direct ascent missile. So it shot at and successfully destroyed one of its own satellites using a kinetic weapon. So it just slammed into its own satellite at high speed. That's exactly what Russia did yesterday, or on Monday. 2009 Iridium Cosmos collision. So here, Iridium 33 is an active satellite. Cosmos 2251 was a defunct satellite, and they hit and had a major debris generating field. This change right here, because we're scientists and engineers, we like to characterize things by, or particularly for astronomers, characterize things by changes of slope, by different power laws and so forth. So we could do that with the space environment. And in about 2015, there was a noticeable change in the accumulation of material in outer space, and that is new space. And then 2019 is where you see this very rapid jump, mainly from SpaceX. That is the birth of mega constellations. I want to emphasize that SpaceX has about 50% of the active satellites, operates about 50% of the active satellites. Weapon tests are a really, really big problem. We have not solved that as of late, although fortunately at the first committee, which worries about global security at the United Nations, the General Assembly is currently in session. A open-ended working group addressing norms and behavior, including security and the possibility of having bans on weapon tests in space, has been established, and that's going to be going for an initial 2 years, and we'll see what can come out of that. Hopefully, there's going to be at the very least a weapon ban for testing debris generating weapons in space, which we do not actually have. I wanted to make an updated plot, what I'm showing here, to show the most recent Russian ASAT test, but I have to use the India ASAT test in 2019 just because I don't have enough information about the Monday test. So what's happened here is each one of these curves represents the orbit through its altitude and phase of a piece of tracked debris from the India ASAT test. That test took place at 280 kilometers, yet debris was transported throughout all of low Earth orbit. And so it threatened all operations in low Earth orbit. And what we did in this particular plot is we then also put the locations of the proposed mega constellations, the Chinese space station, the ISS, to emphasize that this debris generating event, even though it took place at an altitude below the ISS, it still threatened it. The Russian test took place at 500 kilometers, more or less. And so this is just horrible that a state would do this. And we're not sure what's going to happen as a result. Hopefully, this was an issue of the military going a little bit rogue, but we don't know. And this is going to have a strong response, hopefully, at the General Assembly. I am very, very happy to say that Canada at the first committee specifically introduced the idea of a limited test ban on debris generating anti-satellite weapon tests, which is something that we directly called for at the Outer Space Institute. We'll see if it gains any traction. All right, so what are problems with so much material in orbit? Well, there are a bunch. One you've probably heard of is the Kessler syndrome. There are a couple different ways to really discuss it. The way I like to talk about it is that the generation of debris mainly comes from collisions. Okay, there are different extremes to talk about collisional cascades and so forth, but really operationally, it's where most of your debris is coming from collisions. And so you have different rates. You have the rate of collisions with the rate of new fragments that are coming from a higher altitude that are slowly deorbiting through the residual atmosphere. And then just the rate at which things explode naturally, batteries explode, unspent fuel explodes. So you have all these generating materials. So you have collisions, stuff drifting through your orbital shell, and fragmentation. And if that is greater than the rate at which that material is cleared, and the rate which we don't have, but hopefully we will, actively removing debris, then you will have the Kessler syndrome. And that is, you will have then the debris generation being outpaced by its removal, and it will grow. So new space allows for cheap disposable satellites. You hear democratizing space, all good things. But this is coming at an expense. And one of the issues is that it establishes the consumer electronic model, but for space. And so many satellite constellations have actually filed for lifetimes of about 5 years. And so we're talking about tens of thousands of satellites that only have a lifetime of 5 years, but you want to have this ongoing. You're a business, you want to provide global internet, for example, for decades to come. And so there are multiple problems. One of them is, of course, just everything that's happening in order to get those satellites up. So those satellites require launches in order to replenish them. And one comparison that's often used, and I heard it very recently on a panel, is that the space industry produces a minuscule amount of the CO2 compared with things like aviation and other uses, which is true. But that is absolutely the wrong metric to be thinking about. You shouldn't dismiss that metric, but if you're going to make your assessment based on that metric, it's wrong. You're wrong. The issue is that the different types of rockets use many different fuels, and there are many byproducts that come out of these different rockets. I'll show this back later if you want. Some of the biggest things to worry about are the soot that's produced from any type of hydrocarbon fuel. And soot has a much larger impact on the atmosphere than CO2. And CO2 is such an issue with climate change just because we're producing so much of it. But with rocket launches, it is possible to produce enough soot that you swamp all of the CO2 that's produced by general aviation. There are a couple different assumptions that go into that we could get into. But is it possible for humanity to do this? Oh yeah, it's definitely possible. Alumina that's produced by solid rocket boosters, you could produce, and this is alumina and a type of aluminum oxide, you could produce enough of that it actually gets deposited and collects in the stratosphere, that it could contribute to radiative forcing, but it could also contribute to ozone loss because it can allow for inactive chlorine to become activated on the surface of these particles, in which it then goes back in the ozone and destroys a whole bunch of it. The rocket launches, even water vapor, is not totally green, because what water vapor will do is it will deposit water at high altitudes, and that can allow for mesospheric cloud formation. And we don't actually know what the long-term impacts of mesospheric cloud formation might be, but some studies have suggested that with space use transitioning to only liquid oxygen, hydrogen, you would actually double the amount of water vapor in the mesosphere. I'm going to skip, this is an important topic, but I'm going to skip it for the sake of time. Reentries. One of the things that I think, unfortunately, a lot of people have this misconception about is that you burn up all the material in the upper atmosphere and it somehow goes away. That mass doesn't go away. You burn up material from reentries, and now you've deposited all that material in the upper atmosphere. And if you've done it for safety reasons in a way that completely ablates in the atmosphere, then all of that material goes in the upper atmosphere. So again, here are some of the numbers from those mega constellations that I talked about, in which we have about 65,000 of them. They're all having this similar idea of replacing satellites on about a 5-year time scale. They're similar in types of mass and size, so we could actually do some basic calculations here to try to understand what the impacts might be. And I don't really know all the different atmospheric chemistry that's going to be involved with all of this, because I frankly don't know all the chemical composition of the satellites. A lot of that is proprietary. But what we can do is we could do some simple estimates and compare them with the meteoroid population. So meteoroids, some of the best studies out there suggest that there are about 54 tons per day on average of natural material coming to Earth. Most of that is then going to be within still fairly small meteoroids. And this is a distribution that is given in the Sagan 2017 paper, and this is where this 54 tons per day is derived. Other studies have verified this number. So if you have this is our comparison. So if we have 60,000 satellites with about 260 kilograms each, and you're replacing them about 5 years, that's 3 kilotons per year, or about 9 tons per day. So depending on what kind of argument you're pushing, this is either a lot or a little compared with the natural forcing. I actually think you can't ignore that, but we shouldn't stop here. And this is one of the problems that I've had in conversations with some of the companies, is that they actually stop at this point and say, see, this number is greater than that, so we're done. It's not true. Here is the composition of most meteoroids. So if we assume that about 80% of a satellite is aluminum, for example, which is a fairly good assumption based on the alloys and what else might actually need to go into the satellite, then we're getting about 7 tons of aluminum per day. And meteoroids are mostly oxygen. Let's say that again. Meteoroids are mostly oxygen. Okay. And then you have some iron, silicon then as well. And you only about have 0.5 tons per day of aluminum. So we're talking about an order of magnitude more aluminum being dumped into the upper atmosphere from satellites than what we get from meteoroids. And that's going to oxidize into alumina. And then all these studies that are worried about rocket launches now become very important for reentries. And to really emphasize this, alumina has been suggested multiple times for geoengineering, to purposefully dump alumina into the atmosphere to try to make the Earth more reflective as an attempt to solve the climate change issue. It has met huge resistance for very good reasons. But we are going to be doing this completely unregulated as an uncontrolled experiment by just our use of space. There's also the issue if the material does not burn up. And I'm not going to go too much in this, but this is Lottie Williams, who's the only person, well, that's not true. This is Lottie Williams, who was hit by space junk. And she wasn't hurt by it because it had a very large area to its mass. And so it had a very slow terminal speed. But here is a helium tank that crashed into a place in Indonesia. No one was hurt, fortunately. It did cause damage. Here is, again, a helium tank from a Falcon 9 that crashed into Washington State. A lot of people from Vancouver actually saw this reentry. We can actually go on with lots of examples, and we're just lucky that no one's been hit by this yet. But that's another talk. Finally, the impact of the night sky cannot be ignored. So I want you to take a moment and if you will, even close your eyes and just imagine the night sky as you know it, and maybe bring up a memory of what the night sky looks like. But now take that same memory of your picture of the night sky and imagine that 1 out of every 10 stars that you can see is moving. And it's moving because it's not a star, it's a satellite. And that's the world that we will be living in if we have 65,000 satellites at their proposed altitudes. 1 in 10 by itself may or may not seem that bad, but when you say 1 in 10, it's moving, it creates an optical illusion. I've sat on my porch in Tuason here in the lower mainland, which is far enough out of Vancouver that I can see some stars. And during the summer, all night, I can watch satellites go over. And when you see multiple satellites at the same time, it gives you this very weird sensation because the entire sky begins to move. You lose a sense of what is actually fixed and what is moving when you have that. It's just an optical illusion. It goes by, you could shake your head, open your eyes again, and it's fixed. But when all of that's happening, that's a major impact on our natural heritage, on our cultural heritage. We have parks outside of our cities because we live in most of us live in places where we can't enjoy nature, and we have to go somewhere in order to enjoy nature, but we can do that. When you're talking about satellites that completely take over the night sky, you go to a place, you can't escape it. No camping trip will take you to a place where you could avoid the satellites. This is a distribution of the 65,000 satellites S-file projected onto Earth. Canada has a caustic that's going to go across it around 53 degrees. This is going to be a high concentration of satellites simply because it's the turnaround point in the libration on the latitude, just due to the angle of the satellite's inclination. We did some models with my colleague Sam Lawler, and we took a look at 50 degrees north latitude and looked at what the impact would be. So if it's at winter, then we're only really impacted at the nautical dusk and nautical dawn. If we're at midnight, it's actually quite good because of the orientation of the Earth relative to the sun, and then thus the Earth's shadow blocks a lot of the satellites. But if it's during the summer, the 3 hours of precious night that we have in the Vancouver area, we see satellites all night long, just because of that same orientation. And this is when a lot of people are going to go camping because it's going to be summer in Canada and not winter in Canada. So this is the sky that most people will see. We could do this with different types of cuts for the number of satellites you see above or that are sunlit above the horizon. This does not take in any type of magnitude cuts, but we could do this for the December solstice for different latitudes. We could do this for the equinox. And we've highlighted here Chilean observatory. So this is like CTIO, the Hawaii, Canary Islands. And for these lower latitudes, you do get a very sharp cutoff in the number of satellites you see during winter. And then for Chile, we picked about 30 degrees south, you still have a number of satellites that are above the horizon that could be interfering with observations. But if we go to, for example, the Canadian observatories and the number of illuminated sats, like the meteoroid networks and things like that, you basically get no decrease in the number of satellites throughout that are sunlit throughout the day. So that's something we'll have to contend with. And this is directly observable. It's something you can observe right now. So you have, this is from the Rothmy Observatory. And so this is a stacked image over 2 hours. And these are all the streaks that they got in this wide field image. Wide field images are by far going to be the most impacted by this. And I was purposefully observing satellites because I want to know their brightness. And this is a streak that I got through the Plaskett telescope in Victoria. So these things are bright, they're just bright. And yeah, we've heard a lot about mitigation efforts and things like that. And I'm going to skip ahead here. Here's a distribution of brightness that I've measured from Starlink satellites. So the V's here are with the visor sats. So these are with brightness mitigations, and the blue is without any brightness mitigation. If you actually take a careful look at the median distribution of the apparent magnitude or the absolute magnitudes, this is corrected for a range of 55 kilometers. Then there's the visor slats are slightly better, but there's just a huge range, and you have a large fraction of the satellites that are imminently visible. We're also worried about optical flashes. So even CubeSats can be highly problematic if they give optical flashes. And a company out of Rwanda has just filed for 300,000 small sats. One company, 300,000 small sats. We don't know if they're going to just try to sell off the rights or if they're actually going to try to do this. But people want to do like Internet of Things and lots of connectivity using many, many small sats. And so that could be a particular problem if you have 300,000 things that are randomly flashing at night. We've already seen that a rocket body was misidentified as this, what would be a groundbreaking observation, a gamma ray burst at redshift 11, but it was just a rocket body that got in the way of the observation. So we're already seeing these type of things. And while this was a rocket body, this is also pretty far out. Just the addition of objects in space has the potential of increasing the night sky brightness. And that's one thing that we have to be worried about with the number of things that we put up there. And this is the one that we actually have probably the most control over at the moment. And that is, there are a number of activities that are being proposed and pursued that are very obtrusive. One is space-based advertising. Okay, the United States just banned it. This is not widely banned. Other countries could allow it, for example. A Japanese company wants to have artificial meteor showers. And they were contracted to do it for the Japanese Olympics, but they had a failure and it didn't go through. But they just want to inject a whole bunch of buckshot into the atmosphere with different coatings to give you a meteor shower on demand. You could have one at your wedding. Then there's this one is it's created problems at ASU. A student-built spacecraft wants to interact with the public by flashing when you communicate with it. So you could have people communicating with satellites and causing them to flash. So there's no regulation there's nothing that stops you from doing that immediately, because space is free to be explored and used by all states. And that includes companies acting within a state if they're allowed by their state to do the things that they're talking about. So the United States has prevented this Coca-Cola flash thing from happening, but another state may allow that, for example. So this comes down to then interpretation of international law, and at what point are you interfering with other people's use of space? And is astronomy, ground-based astronomy, ultimately protected by the current international law? And that's an open question. But there is quite a bit of reasons for hope. There are some very broad discussions happening, including at the United Nations. There are many issues that have similar solutions or partial solutions. And for example, space debris and light pollution would both benefit by having fewer satellites and by putting things in orbits where they will decay quickly. And while things are moving quickly, like for SpaceX, for example, we're still early in the game, and we can still make very meaningful changes. The thing that I like to point out, Starlink has launched over 1,000 satellites or SpaceX has launched over 1,000 satellites for Starlink, but that's only 1% of what's being proposed. So that's both reassuring and horrific. I went on much longer than I wanted to, but hopefully there's still some room for questions. Thank you.
Thank you so much, Professor Boley. That was awesome, actually. Do we have any, we have time for a few questions. Anybody have any questions for Professor Boley?
I have a question.
Please.
One of the arguments that I hear a lot of the time when I'm seeing people talk about this, like Starlink and other companies, is that people in rural areas need internet, deserve internet for like a quality of life. What is your kind of like what is your response to something like that? Because I'm always just like, I don't know.
No, this is incredibly important question. Thank you, Simone. And I sidestep this issue because it is in many ways a talk by itself. So there's without question a need for internet accessibility by communities, including indigenous peoples who are often cut off. The COVID pandemic has demonstrated this need through telehealth, through online education, and it can show how inequity is amplified by lack of internet access. And the United Nations is making internet access a basic human right. So from the astronomer, how can you be interfering with basic human rights? Well, it's not that simple, of course. The issue is ultimately like, will Starlink truly be accessible to all the people that they're saying that it's going to be accessible to, or is it only going to be accessible to people who are very well off? Will the business model be sustainable? Will it contract? How are these different companies going to be competing with each other? And what happens if you have a single winner that's only authorized in a single nation? So there are a lot of potential problems with just that angle. But then there's an angle that was in a recent Science article that was actually given by the Hoh. This is a First Nation in northern Washington state. And they're early users of Starlink, in which they've been given a Starlink receiver. They've been set up with internet through Starlink, and they're very appreciative of having that. They don't really care about the night sky because it's cloudy for a good portion of the time. And when it's not cloudy, they have Navy planes flying over them anyway. So they've already lost the night sky. So what's it to them type of thing, you know? Which is a problem that we're fighting against. A lot of people have already lost the night sky, right, where they live. But there's a very interesting statement, and that statement is, this is good for now. I'm very much paraphrasing, but what they really want is fiber optics. And when they get fiber optics, they're going to be their own internet service provider so that they could use that as a source of income, and they're going to then have fiber optics for the rest of the rural community. So is this massive infrastructure, this industrialization of space, a stopgap, or is it a solution? And so this is, I gave one example of one First Nation. They're not a monolith. Many people are going to have many different views of this. And I have to emphasize that. But it's, even if we go the rate of saying this is going to give global internet to the entire world, is it really? They haven't demonstrated that.
Those are really good points. Thank you.
Thank you.
Awesome. We probably have time for one more question. Let's see. Oh, Christian. Yeah, please go ahead.
Hello, Aaron. Nice talk. I'm just trying to be the devil advocate.
Please.
When you presented the aluminum example that if you deorbit a satellite to the atmosphere, you put in roughly an orders of magnitude more aluminum in the upper atmosphere, which could be problematic. But I guess they could come back and say, half a ton of aluminum and it's falling for a million of years, and that's not been a problem. So I guess it's more, the issue is more about how it's being processed or how fast it's move around.
Yeah. Thank you. It's an important point to bring up. It's a rate issue, so it does sink, right? So there's only so much that builds up naturally from meteoroids. And so, given that you have these competing rates, you now have an order of magnitude increase in the rates. It is an order of magnitude increase roughly in the atmosphere. So it is different. And there's one thing that I didn't bring up directly that I'm struggling with because I don't know the answer to it. What is the impact of all the other stuff that's in there? The aluminum is pretty easy to go to because it's such a huge component of it. It's been suggested for geoengineering and all this other stuff. But things like titanium, titanium has emission in it has some very bright emission lines in the visible. And we know sodium, of course, there's the sodium layer in the upper atmosphere that is a major component of sky glow for VNR band. If you have changes to things that can phosphoresce, that can actually be a major issue in terms of sky glow. It may or may not be, but there's a huge proprietary component to this that we're trying to work around with getting satellite companies to disclose at least the elemental abundances of what they're dumping into the atmosphere. And that could be a very small amount of mass, but very consequential. And and I don't know what the answer is for that, but a lot of the alloys with aluminum has titanium components at about a 10% level or so, and that's to make it very structurally strong. And so the reason I went for titanium is because it has these emission bands, and it would be much higher than what comes in from meteoroids. So, you know, there might not be a signal there naturally, but we could put a signal there.
Okay.
Awesome, fantastic. Well, thank you again, Professor Boley, for the presentation, and thank you everybody for coming. I just want to point out the next TEPS seminar will be embedded within the 2021 Winter Conference. So if you haven't RSVP'd yet, please do. And yeah, and we'll catch you all next time. All right.
Can I also just say that if anyone wants to talk further about this, they want to know how they can get involved, please send me an email, and that conversation can absolutely continue. Thank you.
Super awesome. Thanks so much. All right, everyone. Take care. Bye-bye.